Hello, this week we're going to talk about angular momentum. So classically, the angular momentum is defined as follows. That is, L, the three-dimensional angular momentum, is defined by x, the three-dimensional vector x, y, z, giving the direction, cross the momentum p, again px, py, pz. So in quantum mechanics, our angular momentum operator is exactly the same thing. It's just that all classical observables get promoted to operators in quantum mechanics. So we have the following. That is, L is still x cross p, but x and p are now vectors of operators. And as I said, this is a general rule in quantum mechanics. Classical observables become operators in quantum mechanics. And this is a straightforward way to form the quantum operator that will give us the angular momentum. So it takes the following form. If we multiply out the cross product, that is, the operator L vector is minus IH bar x cross grad, where this is now we're working in the position basis, and we're also working in Cartesian coordinates. And so we can multiply out x cross grad, and we get the following result. So we have a minus IH bar at the front, and then we have, for example, y, then partial derivative d by dz, holding x and y and time constant, and so on for all these different terms. And we can re-express this as the vector Lx, Ly, Lz, where each of these is the angular momentum operator in each of the three different Cartesian directions. And the corresponding terms are given over here. So we can work with these things as operators and look at their commutation relations, and we find the following. The commutator of Lx with Ly is given by IH bar Lz, and etc. here means that we can do the cyclic permutations to get, for example, Ly comma Lz is IH bar Lx, and so on. So they don't commute. We can't have mutual knowledge of all three angular momenta in all the three different Cartesian directions. It's only possible to have information about one of them at a given time. So notice that this is actually exactly the same structure that we saw when we looked at spin back in an earlier video. So spin, if you may recall, is intrinsic angular momentum, and so it's perhaps not unreasonable to expect that we get exactly the same structure for the usual angular momentum. So here's our commutation relation again. So this means we can't have simultaneous knowledge of x, y, and Lx, Ly, and Lz. In fact, we can quantify this with the Heisenberg uncertainty principle. Remember that for general operators A and B, this states that the uncertainty in A, defined by the standard deviation of the operator, multiplied by the uncertainty of B, is greater than or equal to half of the modulus of the expectation value of the commutator of A with B. So in this case, we find the result. The product of the uncertainties is greater than or equal to h bar over 2, multiplying the magnitude of the expectation value with the third operator. So it's not 0. Actually, there is an exceptional case in which you can know Lx, Ly, and Lz, and that's when all three are equal to 0, which this expression accounts for. But other than that kind of boring case, you can only have simultaneous, you can only know one of the three. However, we can define the following operator. The square of the total angular momentum, L squared, is Lx squared plus Ly squared plus Lz squared. And actually, it's quite straightforward to check that this commutes with all three of Lx, Ly, and Lz. For example, let's check with Lx. The commutator of Lx with Ly squared plus the commutator of Lx with Lz squared, because the commutator of Lx with Lx squared is 0. For each of these two, we can expand them using the relation A comma B squared, commutator A with B squared is commutator A with B multiplied by B plus B multiplying the commutator A with B. And so we get the following. So the sum of these four terms, and sticking in, for example, Lx commutator Ly is IH bar Lz, we get the following result. These four terms, where the first term IH bar LZ LY cancels with minus IH bar LZ LY, and the second term cancels with this term, and we find that Lx commutator L squared is indeed 0. So what this tells us is as follows. So to recap, we have the commutator of any of the Li, where I equals x, y, or z, with L squared is 0. But the commutator of any Li with Lj, where both I and j are either x, y, or z, is not equal to 0 unless for any I does not equal j. So Lx comma Ly here is not equal to 0, for example. So what this tells us is that we can't have simultaneous knowledge of all three components of the angular momentum. We can only have knowledge of one of those at a time, but we can have knowledge of any one of those and L squared, the square of the total angular momentum. You can think of this because classically this would just be the length of the angular momentum vector, so the square of that. And so we can define our angular momentum states with two quantum numbers that can be known simultaneously, one corresponding to any choice of Lx, Ly, or Lz, and the other corresponding to the square of the total angular momentum. So we can write the following. We can define a state L comma m, where L and m are integers, such that the operator L squared acting on this state returns the corresponding eigenvalue. Now, we'll see when we look in more detail at this in a couple of videos' time that the form of the eigenvalue is most convenient to define it in this way, h bar squared L plus 1, where L is an integer here, which is equal to or greater than 0, acting again on the state. And similarly, choosing for convenience the Lz component, we have to pick one of the three, and Lz is particularly convenient as it's the simplest when we write them in spherical polar coordinates, which we'll do in a second. So we get the following. So we can define exactly the same state, L comma m, and it's also got a simultaneous eigenstate of Lz and L squared at the same time. And the eigenvalue of Lz we define as h bar m, where m here is an integer, which it's unfortunate that it's called m because of course we use m for the mass, but this is the convention that tends to be used, so hopefully it's not too confusing that m here is an integer. Okay. I'm sorry, when I said m is an integer on that previous board, m is truly just unrelated to the mass. It's just an integer which we happen to label m. We'll see much more of it in the coming videos. Okay, so let's look at spherical polar coordinates. So still in the position basis as we were in the Cartesian coordinates, we can define spherical polar coordinates are theta and phi in the usual manner. An azimuthal angle coming down from z, the radial distance, and the polar angle phi, all in the usual form. Then if we just write out the components of the angular momentum, defined as before as x cross p, or minus ih bar x cross grad, we find, I'm only going to write the Lz component because it's the simplest to write. That is, in this position basis, in spherical polar coordinates, the Lz operator is minus ih bar d by d phi, holding r and theta constant and time. Lx and Ly are a bit more complicated, but it's not too hard to work them out. And it's also convenient to write down the L squared angular momentum operator, which comes out as the following. And the partial derivative subscript notation is coming into its own here as things are getting a little bit painful to write down. It's worth noting that the angular momentum, the units of angular momentum, are actually exactly the same as the units of h bar. And so it's easy to check whether we've got the right power of h bar in our expression. And another thing worth noting is that the Hamiltonian can be written as follows. So the Hamiltonian, in the position basis in spherical polar coordinates, acting on psi of x comma t, where I'm really writing psi rather than the usual phi of just x, just because phi is being used now as our polar coordinate. is equal to minus h bar squared of 2m grad squared plus v of x acting on psi of x and t. And expanding the grad squared is the thing that differs in this case from Cartesians. We get something which acts only on the coordinate r, plus the L squared operator over 2mr squared, plus the potential written in spherical polar coordinates, all acting on psi of x and t. Having knowledge of this L squared operator is particularly convenient. We'll see much more of this when we come back to study the hydrogen atom shortly. Thank you for your time.